billion years. It's a wonderful place to live for all of us. Even when we look at the planet as this pale blue dot and close up as a water world, we have to remind ourselves that the Earth's resources are finite. And these are some images from the artist Adam Neiman. On the left, you can see all of the water at the surface of our planet gathered up into a ball. And on the right, you can see our atmosphere gathered up into a ball. And you can see how finite they are. If you want a comparison between the thickness of water compared to the thickness of the rest of the planet, it's much, much thinner than the skin of an apple. And of course, it's this water and this atmosphere which sustains life on planet Earth. These are finite resources. Nevertheless, many people suggest to us that if we do damage to the Earth, and of course we are, there are other places that we can potentially go and inhabit in our solar system. Venus, of course, is our nearest neighbor. It's just been in the news recently because there's the suggestion, it's an old suggestion, of course, that there might be life persisting in its atmosphere at temperatures and pressures similar to the ones that we have on Earth. It's certainly not really a place that we want to go and live, though. This is Russia's Venera 13 spacecraft. This is an image taken on March the 1st, 1982. Venera managed to survive about 2 hours on the surface of Venus, where, of course, the atmospheric pressure is severe and the temperatures are around about 470 degrees Celsius. It's not really a place that we want to try and live as a terrestrial species. Another place which is often mooted, that we can potentially run away to, is Mars. And of course, Mars for a long time has exercised our imaginations as a place that might have been inhabited in the past. These are the lines that the Italian astronomer Giovanni Schiaparelli drew in the 1870s, now obviously known to be an optical illusion. But these fired the imagination of businessman Percival Lowell, American businessman Percival Lowell, who thought that these were perhaps irrigation systems connecting together vast cities, the last attempt of a sophisticated civilization to resist the rather dry habitat of the surface of Mars. Because this is not a place that we want to run away to either. It's a very cold desert, very little water, and an atmosphere, of course, which isn't breathable. Why would we want to leave the wonderful planet that we live on to go and live on these other worlds, which are nothing by comparison? Back on Earth, something pretty fundamental is happening. If you were an alien civilization passing on the dark side of planet Earth, over the past couple of 100 years, you will have noticed something very significant happening, because the night sky is now ablaze with the lights of hundreds of cities with more than 1 million inhabitants. And now 33 of these cities have more than 10 million people living within them. And this is a growing phenomenon. And you'd be able to understand from that something very significant had happened on planet Earth. Significant in terms of energy use, but in terms of population growth also. Humans have significantly modified the surface of our planet. We move more Earth, an order of magnitude more Earth than every river on planet Earth. You can see the figures there. It's an astonishing figure for a single species to be able to undertake in a year. It's not just that we move sediment around, we use a considerable amount of water, 10,700 cubic kilometers of fresh water every year. Or that means we would be emptying Lake Malawi in Africa every 9 months. That's a gigantic lake. Or to bring it a little bit closer to home, we would drain Loch Ness every 6 hours in terms of our utilization of water as a species. Again, a staggering figure to think about for a single species. We use vast energy resources. It's currently running at somewhere around about 900 exajoules per year. That's a vast figure that I find difficult to actually comprehend. That's a combination of the energy we use from primary resources, but also from vegetation. Maybe to encapsulate that in a way that's clearer for us, if you imagine a 60-watt light bulb, it's got to stay lit for 450 billion years to burn through a single year of human energy consumption. And of course, the universe is only 14 billion years old. So your light bulb basically has to burn until the end of time. That's led many to speculate, in fact, that humanity is actually running down the Earth's reserves of chemical energy, that the Earth battery is running down and that we are dissipating that energy out into space. Of course, as part of that process, we're also reconfiguring the atmosphere. We typically are putting about 37 billion tons of carbon dioxide into the atmosphere each year. And again, that's an order of magnitude greater than anything from natural processes. You can see there the approximate figure for volcanoes. And I'm sure, again, you've seen this in the news recently, humans are reconfiguring the biosphere. Indeed, we are at the beginning stages of a potential mass extinction event. We're not yet within it, but we are severely reducing the environmental ranges of 1 million species. So we're at the precipice. So in terms of air, water, land, and life, we are very significant agents of change on planet Earth. And those changes are accelerating. So if you look, for example, at the way in which we've released carbon dioxide to the atmosphere, or the way in which we use coal and oil, gas, cement, then most of that usage has been in the past 70 years. 85% of CO2 emissions, for example, have happened in the past 70 years. So this is a very, very rapidly changing situation. And so there's a group of us, Richard said, I'm part of the Anthropocene working group that's actually trying to define a new epoch series of geological time in the geological column. And we think that that will be established probably in the middle of the 20th century, because as you can see here, just from this simple graph from my colleague Colin Waters, there are a whole series of major changes in things like radiogenic isotopes from the A-bomb tests in the middle of the 20th century that can mark this interval everywhere. But also things like our cumulative production of concrete or our production of plastics, which have accelerated so dramatically during this period. So this is what we're mooting as a potential new geological boundary. I want to ask how we've got here, and I want to ask two follow-up questions to that. How have we changed things? And how must we change to survive? Because the degree of change and the rate of change is now so great that we as a species are threatening the entire Earth system. And I hope to be able to convey that to you during this talk. So three main points. How have we arrived at this state of domination? How have we actually changed things? And I'm going to focus very much on the biosphere and life there. And how must we change to survive? Let's begin then. How did we get here? It's a fundamental question of geology. And actually we have to begin by asking the question, what is it to be human? So here we're looking at probably the most famous painting in history of Leonardo da Vinci, obviously, of the Mona Lisa. When we look at the Mona Lisa, we don't just see the image. We actually are trying to look into her eyes and we're trying to guess what she's thinking. It's something that we do as a species. We want to relate, to try to understand what others are thinking about. And this is part of our cognitive fluidity. It's an idea very much developed by archaeologist Steve Mithen at the University of Reading, that we, unlike other primates, are able to connect different components of our brain so that we can share ideas across it, and it allows us to be incredibly creative. We can see how that maps out as we go through the physical record of humans over the past 3 million years. Because this begins really with us beginning to walk upright over 3 million years ago. Not humans, in fact, but in our close relatives, the Australopithecines, the southern apes that we're probably derived from. We begin to make tools, of course, because standing upright, we're now freed to be able to do that. We're not the only tool makers, many other species do as well. But of course, we're the only tool makers that have really developed this to an incredible degree of sophistication over the past 3 million years, which has allowed us to control our environment. we begin to leave our skeletal record in the rocks. The earliest human, ancestral human, has left its record about 2.8 million years ago in Atha and Ethiopia. We think this is Homo. It's our genus. We have to jump forward rather a long way, 2.5 million years, to northern Morocco, where 300,000 years ago we can find the record of anatomically modern humans. So Homo sapiens that look like us, but we don't know necessarily at this stage whether they're actually thinking like us. They haven't left any evidence to really suggest that. We have to jump forward again in time, another 200,000 years or so, to find evidence that we're beginning to think in a kind of modern way. So here are the first inklings of that. These are scratches on pieces of ochre found on the floor of the Blombos cave in South Africa. They seem to be abstract designs that suggest the development of this cognitive fluidity, that we're beginning to see the world in different ways. And of course, linked to this also are major changes in our ability to use and develop technology. We jump forward in time a little bit further to about 40,000 years ago. We start to find widespread evidence of art from Europe to Indonesia, in a way in which we're clearly relating to the animals around us. And indeed, my cat has just brushed past my feet, so I hope he's not going to jump onto the table. He must have heard that. These are some of the beautiful cave art depictions at the Altamira cave in northern Spain. And many people have interpreted this as our species, our cognitive fluidity, actually trying to get into the minds of the animals that we relate to in the environment around us, perhaps as a way of understanding them and maybe facilitating the way that we could track them and hunt them more successfully. There are many different explanations for what might be going on here, but this is one of them. And it's certainly the case that by then, by about 13,000 years ago, we have become a major influence in the landscape. Wherever humans enter new landscapes, in Australia, in Europe, and in the Americas in particular, we have a considerable impact on the fauna there, particularly of other large mammals. This is what's often referred to as the megafaunal extinctions of the late Pleistocene and early Holocene. And of course, it's ongoing at present also, because we also threaten the well-being of these animals as a species now also. So increasing evidence of our impact on the biosphere. Around about the same time, we start to develop agriculture, and from around about 11 to 12,000 years ago, and we begin to domesticate animals. And that appears to begin, first of all, in a fertile crescent between the Levant, Anatolia, and the Euphrates and Tigris rivers. And almost simultaneously, and of course, naturally, if you think about it, we start to live in towns. If you start to produce agricultural surplus, it's not something you can really carry around with you. You need to develop a sedentary lifestyle. Well, this is Çatalhöyük in Anatolia, and it dates back 9,000 years. And of course, these archaeological sites are now revising a whole idea about how long we as a species have lived in cities. We've been living in towns for 11,000 years, since the foundation of towns like Jericho, and a little bit later, Çatalhöyük. And there's a wonderful reconstruction of Çatalhöyük. I love this. This is what it looked like about 9,000 years ago. To me, it's a bit reminiscent of a kind of seaside chalet park, if you'll forgive my humor here, but you have to think of people living here for 1,000 years. This was a settlement that was sustained for 1,000 years. It was viable for all that time, but it seems to have failed, possibly because these people over-exceeded the produce in their local environment. So that's a lesson for us to think about as we go forward, because it's a recurrent theme in urban civilizations. So Çatalhöyük survives for about 1,000 years, and then it disappears from history until it's rediscovered by archaeologists. A little bit later, we start also to see evidence of perhaps a changed relationship between humans and nature around us. So this is a master or mistress of animals. this kind of insignia appears in lots of different cultures, and you can see a human figure between two animals. It's as though the human figure is actually in control of those two animals. This is the oldest one of these master or mistress of animals, from about 6,000 years ago in the Mesopotamian town of Gersu. But it's a recurrent theme, and it suggests now that perhaps humans are thinking that they are in control of the biosphere around them. It's a different kind of way of depicting these animals from what we saw in the cave at Altamira. Not long after, we developed writing, and of course that was very important in terms of imparting information down generations. It led to incredible leaps in technology, and those technological leaps have been accelerating very rapidly. This is the Iron Bridge, of course, in Coalbrookdale in Shropshire, and 200 years ago it was the broadest metal suspension bridge anywhere on planet Earth. It's got a span of about 60 meters. Very impressive in the late 18th century. This is the Akashi suspension bridge in Japan. It has a span of 4 kilometers. It's the longest bridge in the world. And we managed to do that technological leap forward in 200 years, which is an incredible feat of technological innovation in a relatively short space of time. And part of this process that I tried to make the point near the beginning of this, of an accelerating process. Of course, we've also engineered the means to feed billions of us. We have the Haber-Bosch process, which fixes nitrogen so that we can fertilize these crops. And we've had the Green Revolution, which has rolled out crops across the world, which we can mass produce to feed vast numbers of us. And indeed, there are vast numbers of us as a species. I was born in 1965, and in my lifetime, human population has more than doubled. There are now, it's actually difficult to keep up. Every time I find a new graph, it's out of date within a year. There are 7.8 billion of us on this planet. We add the population of Germany every year. This too is an accelerating process, and it's had a very significant impact on the rest of the biosphere around us. So there are 7.8 billion of us living on this planet. That's a difficult figure to comprehend. I certainly struggle with 7.8 billion. I want to break this down into smaller packets that might be a bit more manageable. And also to make the point that whatever happens in the future, there are so many of us on this planet that we'll almost certainly leave a pretty good fossil signature of our presence here. There's about 470 million tons of us walking around at any point in time, and about 75 million tons of skeletons. So a good chance that we will leave a physical record of ourselves long into the future. Let's break down that figure though a little bit more. Let's come down to an individual city. Let's take a mega city like London. The metropolitan area is about 14 million people. Still a huge sum to think about, difficult to comprehend. Let's come down a little bit more to a town that I'm sure many of you know. This is Carlisle, about 75,000 people. You can get a sense, I think, of those people. You can see the boundaries of Carlisle, so we can kind of grasp that number. And then somewhere that I think you normally have your meetings. So I would love to see Kendall this evening, but of course it's not possible. That's just got about 21,000 people. Why am I doing this? Because I want to give you a comparison between you as a species and your numbers and our primate cousins. And I want to ask you, how many cities do you think our primate cousins can actually build? Let's have a look at some of the total wild populations of some of our relatives. And excuse me for 1 second, I have to open the door because my cat is going bonkers next to me. Okay, he'll be happy now. Okay, let's look at some of the total wild populations of some of our relatives then. The next two most populous ones after humans is Muller's Bornean gibbon, perhaps as many as 400,000 of those in the wild. That's the next most populous species. That's one city. Bristol, it's about the size of Bristol, the next most populous species. After that, it's the iconic chimpanzee. That just about makes the population of Leicester, about 300,000. So both of these populations of medium-sized cities. Let's come down the list a bit more. The Bornean orangutan, 50,000. That's Carlisle. The Sumatran orangutan, 14,000. That's Kendal. That's its entire wild population. And the beautiful and mournful golden lion tamarin, looking at you, just 1,000, one village. The point I want to make to you is that you are numerically much more than 99.9% of all primate individuals on this planet. One species is more than 99.9% of all the primate individuals on this planet. And that is remarkable for a single large mammal species. Those numbers are probably unprecedented. So really we have very fundamentally changed our relationship with the rest of nature. So let's have a look at how we've changed things. Let's develop this theme a little bit more. And in particular, I want to show you how we have completely reconfigured the biosphere into a different state than it's ever been in for 4 billion years. So really a very, very significant change. So I'm going to focus on the biosphere because there isn't really time to look at all the different components of the Earth system, but actually our impact is fundamental wherever you look. Part of this, of course, relates to the way in which we are expanding our energy consumption. And we're expanding our energy consumption also as we transfer from a rural to an urban species. We're now a dominantly urban species. And that happened actually in the early part of this century, around about 2005. It's an accelerating process. So we gather huge amounts of energy from the Earth system to support all of our numbers. It's not just primary energy resources though. I want you to think about the energy resources we garner from the biosphere around us. So this is a figure published a couple of years ago in a paper that shows the distribution and density of animals that we eat, that we utilize around the planet. If you just look at cattle, for example, there's a huge density of them in the Americas. And of course, cows were only introduced into the Americas at the time of Columbus. So this in itself is a wholesale reconfiguration of the biosphere in the Americas from the way in which we've introduced new organisms and then we've proliferated those organisms. In Brazil, for example, there are enough cows for every single member of the population to have one cow. Around about 210 million cows wandering around in Brazil at present. And you can see it's the same for many other of these domesticated animals. Such that half of the habitable land that's habitable for us and all other animals and plants is now used for farming. And 3/4 of this farmed land is used for animals and dairy. About 1/3 of the land that's under crops is also used to feed those farm animals. So a very, very considerable part of the land is utilized to feed our pastoral animals. And then of course we then feed on those. So that's a wholesale reconfiguration too. And I have to give you some figures because it's important to contextualize this. You need 170 meters squared of land to produce 2 meat patties. So you can see that very rapidly, the amount of land you need, you think of the number of meat patties that are sold every single day, is very, very considerable. And so I wanted to conceptualize that in another way. And there are 2 chains of burger restaurants that I'm sure you all know. And they're the 2 biggest ones on the planet. One has 38,695 outlets and the other has 18,786 outlets. So let's guesstimate that each restaurant is about 400 square meters, about 20 meters by 20 meters if you take the car parks and such like. That means that actually if you stand them all back to back, they will cover an area of 23 square kilometers, which is pretty impressive actually. So 23 square kilometers of burger joints on the planet. So again, you need to factor in just how much that is factored into the consuming the amount of landscape that is needed to facilitate that. It is huge and it is vast. And that's just one part of our food system. I'm going to come back to this again a little bit later. And this really is part of the great pressure for land that we are putting on the rest of life. We are leaving the rest of life with too little space. And as a result, I know Richard was telling me that he'd been watching the program of David Attenborough a couple of weeks back. And David Attenborough was talking about this, of course. But we can plot up the increasing rate of extinction of a whole range of different organisms, and it is accelerating very rapidly. And again, as you can see from this graph, this is an accelerating process, so that we are potentially approaching a mass extinction event in the not too distant future. These are some evocative recent extinctions. Some of these I'm sure you'll know about. There's the dodo, of course, which went extinct within 3 decades really of being sighted for the first time. The beautiful Caribbean monk seal that disappeared in the middle of the 20th century. The wonderful Yangtze dolphin, which has not been seen for 80 years. And down there, bottom right, is the smallpox virus, which was extinguished in December 1979. They're very evocative, but they don't really leave a very distinctive geological signal for me. Of course, what we also know is that extinction is not unique. This has happened many times in the geological record. There have been at least 5 mass extinctions in the past 500 million years. So although this is going to be a major component of what we might potentially do to the biosphere and the Earth system going forward, it's only part of the story. In fact, the changes that we are enacting are considerably greater than this. And I hope I'm going to be able to show you that over the next few slides. So how to measure our impact on the biosphere? It's not just extinction, it's actually much greater than that. There are really 4 unique changes, and they're unique when measured against the entire history of life on planet Earth. I don't think that it's possible to recognize these state shifts at any other point in the fossil record that I'm aware of. So let me talk you through these 4 unique changes. The first one is one that we've alluded to, that we as a species take a huge amount of energy resources from the biosphere. And these are some figures from Václav Smil. And you can see down there, humans and their domesticated animals equal 175 million tons of carbon, dry mass, that's the way it's measured. Wild mammals are less than 5% of the terrestrial mammal biomass. Wild mammals are less than 5%. We and the things we eat are more than 95%. I think that's a very, very strange relationship that I don't think is present anywhere in the geological record. If you look down at the very bottom, those little tiny figures, it says that we take something like 1/4 to 2/5 of all net primary production. That means we're appropriating up to 2/5 of all of the energy stored in plants on the planet each year, which again is a staggering figure for a single species. Of course, we then supplement that with our primary energy reserves, and those have been doubling. You can see the figures there. 1 million tons of oil equivalent. It doubled between 1973 and 2014. So we supplement this energy we take from the biosphere with fossil biosphere energy, if you like, from coal and oil and gas, and other sources also. And this is also unique because as a terrestrial species, we don't just dominate the land, we also dominate the oceans. No other species has done that in the history of our planet. And there's a figure down there, you'll see 2016, because that's the peak figure. Total world fisheries were 171 million tons. And the really appalling figure is that 1/4 of all the fish that were landed went to waste in the supply chain. So we're wasting vast amounts of food also. And of course, this is also unsustainable. It's unsustainable because you can see from this figure published about a decade ago that our impact on many places where fisheries would actually be naturally very abundant is now very severe. They're the places you might expect. So the coast of North America, the coast of Europe, and the area around Japan, for example, there to the south of Kyushu and Shikoku Islands, and is very, very severely fished, such that many fish stocks, at least 1/3 of fish stocks now have been fished almost to oblivion. That's the first point I want to make to you. So we've already changed the relationship that we have with the biosphere in a way which is completely unique in the whole history of our planet, but it's only one factor. Let's have a look at the invasion of the body snatchers now. And here I'm showing my love for 1950s daft movies. not really the body snatchers, but actually the ecosystem snatchers, because this is the way in which we've relocated species, including my cat, which is still lingering somewhere in the near vicinity. This is something that's happened before. If you think about the Great American Interchange, for example, 3 million years ago, when the Americas were joined at the Isthmus of Panama, animals went north, animals went south, and that's recorded in the fossil record. But we're doing this at a global scale, and that's unique. Invasive species are everywhere, even in isolated islands in the Pacific, and that's unique. We've been doing this for some time. So if you think about the translocation of maize, first cultivated in Mesoamerica about 8 to 9,000 years ago, it's been translocated across the world over many millennia and centuries. And it's left a physical record of that in the geological record that I'll show you in a moment. We often don't notice the damage that invasive species do. They can be very, very damaging in a whole range of ecologies on planet Earth. We don't notice things until they start to harm us. And of course, this is an invasive species. This is the coronavirus, COVID-19, and it too is reconfiguring our human ecologies. It's the reason why we're meeting online this evening and not physically in a room. It's an invasive species and it's changing the way our ecosystems function also. And of course, it's being facilitated in its movement by global transportation networks. This movement of species is actually smearing biogeographical boundaries. This is Alfred Wallace, of course, and he was very formative in developing our ideas of evolution. And here you can see the Wallace line between the island of Bali and Lombok in Indonesia. It's a major biogeographical boundary, denoting different fauna and flora either side. But that boundary is now being smeared. I have a PhD student working on this at the moment, although obviously her fieldwork is now interrupted. So this is Rachel's work, one of my PhD students. And this is just looking at golden apple snails, which come from Argentina and have now rampaged across Southeast Asia. They really couldn't care less about these ancient biogeographical boundaries. You can see that this particular species extends all the way across to Papua New Guinea, and it has a major impact on human cultivated ecosystems, on rice paddies, can be very damaging to them, so can damage people's livelihoods. Birthplace of humanity, the East African savanna, is also wholly reconfigured by humans. At least 245 invasive plant species in the Serengeti Mara savanna ecosystem of East Africa. These have left a physical record too. So we decided we would introduce pine trees into Africa at the beginning of the 20th century. They're not native to this region at all. And that's left a distinctive record. So if you go to Lake Baringo here, you can actually find a biostratigraphical record in the palynological record preserved in that lake from pine trees. You can see pinus there, I hope. And you'll also probably see Zea mays there, which is the introduction of maize a couple of centuries earlier. So both of these have left a physical stratigraphical record of the human impact on the biosphere that geologists, of course, should be able to recognize long into the future. Even geographically remote islands like Hawaii have been invaded too. Forgive me for a second. So of course, these are regions that really can only be invaded with the help of humanity. If you look at New Zealand there at the top, it's from a classic study of McNeely from a couple of decades ago. You can see that the number of invasive plant species equals the number of indigenous species. And that's almost the case in Hawaii too. So let me take you to Hawaii. This island, along with most of Polynesia, began to be colonized in the 13th century. It's a very rapid period of extension of Polynesian peoples across the Pacific. And they brought with them a whole series of animals and plants. They brought with them the Pacific rat. And we can find evidence of the Pacific rat in the fossil record of the Hawaiian Islands. It's not just Polynesian people, though, that helped to reconfigure the ecosystem of the Hawaiian Islands, because later European settlers decided they would bring in their own range of organisms also. So we introduced the giant African snail, and then we introduced the cannibal snail for good measure as well. And of course, you can guess what happened to the local indigenous snails. And that too has left a very distinctive fossil record. So here on this figure, you can see the pre-human, and then the Polynesian invasions, and then the kind of European invasions. And here, Aschatina filica and Euglandina rosea, those are those two snail species. And you can see that all of the indigenous snails have gone extinct. So a very distinctive pattern of complete faunal turnover here, of extinction of the indigenous snail fauna at the expense of the introduction of new snail fauna. Very distinctive stratigraphical signal of this. Another one of my species is working in San Francisco Bay. And here something very fundamental has changed. In fact, the entire bay assemblage is basically being replaced by invasive taxa. There's almost nothing left of its original ecosystem. And this has happened in the past 150 years. So Stephen's lucky, he goes out with the United States Geological Survey, or at least he did until COVID-19. And he goes and drills in the bay, brings up his core, and then he investigates the fossil record of invasive species in those cores. So this is one of the mollusks that Stephen finds in his cores. It's now very prodigious in the bay. This is the Amur River clam. And of course, the name is a giveaway because the Amur River is the river that marks the boundary between Asiatic Russia and China. So what on earth is the Amur River clam doing in San Francisco Bay? It's not just there in small numbers, it's massively invasive, and it's completely reconfigured the bay ecosystem. It's one of many. So here we're plotting up all of the different invasive species into a kind of theoretical biostratigraphy. You can see P. amurensis here, I think. That's the Amur River clam, and it arrived in 1986. And actually we can track back and we can find these species. We try to find them. Stephen's trying to locate them in order in the cores, and so far it's following the observed patterns are being replicated in the order of appearance in the core. So we can actually make this theoretical stratigraphy into a real biostratigraphy. And this is a proper invasive species. So this is the Amur River clam, and it just completely takes over the ecosystem. And you can see that it's actually so prolific as a filter feeder that these clams are able to filter the entire water column of the bay once a day in the northern part of the bay, which is staggering for a single species. And it means that it's utilizing the food supply of many other organisms. And at the top there, I hope you can see reached abundances of up to nearly 20,000 individuals per square meter of seabed in the bay. It wasn't there 3 decades ago, and now it's totally changed the fauna. Just to emphasize, this is Stephen's work, my PhD student, Stephen Himpson. Okay, I've given you 2 factors which are already fundamentally different from anything that's happened in Earth history before, but we're only halfway through. Modified landscapes, or anthromes. This is very much the work of Earl Ellis at the University of Maryland. And this is the way that humans have wholesale reconfigured ecosystems on planet Earth. And Earl has actually made a very nice plot which shows you how we've changed the terrestrial landscape. So there you can see 1700, we've got used ecosystems, which would be things like intensive agriculture, urbanization. We've got semi-natural, which could be things like pasture lands with some kind of original ecosystem remnants preserved within them. And we've got wild ecosystems where there's very limited impact. And you can see that even here in 1700, 50% of the landscape is already human influenced. Let's go forward 300 years, and you can see that now 75% of the landscape is altered and 50% is used. So that's really very fundamentally changed. And there's been an update to this work, a paper just published a year ago, which is now saying that 95% of the ice-free landscape is human impacted in some way. So we are everywhere. We are everywhere to the degree that you can say this: the world is no longer dominated by natural ecosystems with humans disturbing them, but instead is dominated by human systems with remnants of the natural biosphere lingering within them. That is a very fundamental statement, which means that we are now wholesale in our impact on ecosystems on the planet. Of course, it's not just the whole ecosystem, but it's the organisms within that ecosystem. We modify them at a very fundamental level. Our technology has advanced to the stage where we can even think of translocating genetic systems from one plant into another to increase its productivity. Stone tools to super plants. Some of that may be extremely important in terms of feeding people as we go forward. But some of the things we do to the biosphere, I think, are not really super at all. This is what we've done to chickens over the past 5 decades because we like eating them. And we've increased their individual biomass 4-fold, so that the average broiler chicken can only live for about 6 weeks before it actually, its neck breaks under its own anatomical weaknesses, compared to the jungle fowl ancestor that would live for many years in its wild habitat in the jungles of Southeast Asia. Not such a good thing to do to chickens. And we eat 63 billion of them every year. And there are 23 billion of them alive at any point in time, which is an order of magnitude greater than the most abundant wild bird, the red-billed kalia, which is about 1.5 billion in its population. So a very fundamental change again. And actually that too has left a potential stratigraphical record, because as you can see, the dimensions of the bones of modern broiler chickens are quite different from those of previous generations of domesticated chickens. Change 4 is perhaps the most fundamental of all, and this may be a concept that you've not heard of before. It's very much the idea of Peter Haff, who's a part of the Anthropocene Working Group and is based at Duke University in North America. The technosphere is a sphere like the biosphere, the lithosphere, the hydrosphere, and the atmosphere. It's everywhere on our planet. It's developing out of humanity. It's us, our technology, our artifacts, our social and technological networks. There you can see trade routes for commodities, for example. That's, if you like, the arterial system of the technosphere. And it's an emerging complex system which is self-propelling. It is out of our control. None of us as individuals, none of us as political systems, no state has power over this system. It is self-propelling. And actually, we are now unable to stop it because it is so large and it is so integrated. Let me give you a sense of that. So it is everywhere. Everywhere you go on this planet, you can find a technosphere. The problem with the technosphere is that unlike the lithosphere, the atmosphere, the biosphere, and the hydrosphere, it hasn't had a long time to co-evolve. Those other systems are self-sustaining by the way in which they have evolved together over a long time frame. The technosphere is not. It's spiraling out of control, and it's a real problem for us as we go forward, as I want to show you. Let me just give you an idea of technospheric consumption. So the USA, the country we associate with the skyscraper, used 4.5 gigatons of cement to build skyscrapers in the 20th century. And China does that every 2 years in the 21st century. That's a massive acceleration in the technosphere's consumptive patterns. It's huge. If you try to measure it, so you take cities, pasture land, croplands, trawled seabed, transportation systems, it weighs about 30 trillion tons. It's a gigantic entity in itself. So it's truly a sphere of the Earth system. It's associated with an explosive diversity, with a whole range of new species. Literally millions and millions of them evolving, not in a Darwinian sense, of course, more in a Lamarckian sense, to fill the kind of ecologies that have been engineered by humans. And its energy consumption is absolutely colossal. If you take its combined energy consumption, both from primary resources and from the biosphere, it's now approaching the amount of energy that is produced by plants each year growing at the surface of our planet, which means it's not sustainable in its present format. So now it's appropriating nearly as much from the Earth system as the above ground component of terrestrial vegetation produces in a year. Clearly that's not sustainable. It's had some huge impacts on the way we live. It's caused the massing of people in huge cities, first of all in London perhaps. And that's actually produced some very interesting geological structures that will preserve long into the future. This is a trace fossil system that burrows under London, and it's incredibly complex, of course. It's an order of magnitude larger and more complex than anything in nature, but of course, this burrows into geological strata. It's a permanent feature. This will be there millions of years into the future as a physical record of us. And of course, it's expanded very dramatically. In the space of 15 decades, really, these systems of transport have developed across the world, and they will leave a distinctive geological signature of humanity long into the future. It's another Anthropocene signature. There are other signatures too, because the biogeographical patterns of our cities and cultures is also changing. If you go back a century, if you're time travelers and you visit any of these countries, you'd know you were in Germany, you'd know you were in Saudi Arabia, you'd know you were in France. Just by looking at the architecture, it would be very clear. So 9th century England, that's Brixworth Anglo-Saxon Church, not very far from me. 9th century Vietnam, beautiful Hindu temple there. You know exactly where you are on planet Earth. Now tell me which one's London and which one is Ho Chi Minh City. You know, of course, the top one is London because there's Tower Bridge, but they're almost identical. They're built from the same materials, from steel and glass and plastic, and that has left a distinctive stratigraphical record of these changes in the mid-20th century as we started to trade commodities globally. Plastic, glass, steel, that's what these cities are made from, and concrete, of course. Okay, I've spent a long time trying to tell you how we've got here and how we've wholesale reconfigured the Earth system. I focus very much on the biosphere, though I could have also talked about the other components and how we've fundamentally changed those two. And I hope I've convinced you that the changes are really very fundamental, and they're fundamental even by any measurement of any other stage in the biosphere's long history. So I want to finish up by asking all of us how we must change our behavior to survive. And it really is a question of survival. And it's a question of survival in the near future. Now, a couple of years ago, I understand that one of my colleagues, Derek Sivitzer, came to speak to you about the Chengjiang biota. And these are these wonderful fossils in southern China. I'm lucky enough to work on these too, that preserve all of their soft anatomy. And a couple of years ago, we described this fossil from 580 million year old rocks. It's a worm. I hope you can see that. It's got its gut trace. That black line down the middle is the gut. But I hope you can see that the big worm has a whole series of little worms clinging to it. This is the first record we have anywhere in the fossil record of an intimate symbiotic ecology between two different organisms that are intimately connected at the integument, at the skin level. It's the first example. What do you think this relationship is? Normally I'd ask you to comment in the room, but I can't do that. So I'll give it away. Do you think this is a mutualistic relationship? Do you think the two are cohabiting and are giving each other something useful and they're quite happy about this? Or do you think it's parasitic? Do you think the little worms are hitching a lift and blood sucking from the big worm? I think it's probably the latter one, sadly. The point of showing you this, though, is that complex ecological relationships, symbiosis, mutualisms, parasitisms between organisms have been evolving in the Earth system for hundreds of millions of years. And they've allowed ecosystems to develop complexity and a range of resilience that means that those ecosystems can function in a very good way in terms of the way the energy flows through them, and are also good in the way in which they're able to recycle materials to sustain them over long time frames. Unfortunately, I think that the human relationship with the rest of the Earth system is really told in this wonderful picture from Hieronymus Bosch, who's one of my favorite artists because I like Flemish paintings. And in this triptych, you can see three scenes painted around about 1500. On the left, you have the Garden of Eden. Okay, you could say that's our hunter-gatherer past when we lived quite happily, mutualistically with the rest of the Earth system. In the middle one, oh dear, we seem to have decided that we can consume the Earth's earthly delights with impunity, and there will not be any problem for us whatsoever. We all know intrinsically that that's not the case. Because if we carry on like that, we're going to head into the right-hand panel, which of course is a depiction of a hellish scene. And we need to avoid that at all costs for ourselves, but also for the rest of the biosphere. And just focus on that hellish scene on the right, because 2 years ago, I was unfortunate enough to go to this place. It's called the Dandora Tip. It's in Nairobi. And it's where all the rubbish for the city is dumped. And it's an example of where we go if we use up all of the Earth's resources. Life on a used up planet. Even here, in this terrible environment, people are eking out a living. You can see there are pigs. There are the gaunt marabou storks, which look like something from an Hieronymus Bosch painting. People are still eking out a living here. It's a terrible place, but you know, even in this terrible place, life is clinging on. And this terrible place is still a damn sight better than being on the surface of Mars or being on the surface of Venus. So we really do need to think about how we preserve this wonderful planet that we live on, not think that we can escape somewhere else. Humans have developed a parasitic relationship with the rest of the biosphere. It is pure and simple. We are utilizing the biosphere's resources. We're not giving much back. This is a parasite, and it's a very severe parasite, and we have to change this relationship. We don't even recycle materials that would help us to sustain that system over a long time frame. So we're the worst kind of parasite. We're not only sucking the energy out of the biosphere, we're dumping all our rubbish onto it as well. How are we going to function going forward if we carry on like this? We know that population is going to grow and that cities in particular are going to grow. This is a dystopian view of Los Angeles in the original Blade Runner film from 1982. It projected a Los Angeles in the year 2019 with 119 million inhabitants. And that didn't happen, of course. But some city projections suggest that that's where we're heading in the late 21st century. So Lagos, for example, is projected to have a population of 88 million. And several other cities are suggested to be on this trajectory. How will cities, all cities, function in the biosphere in a mutualistic way? That means they don't destroy the biosphere around them when they are on this scale. We have to evolve these mutualistic relationships very, very quickly. Because if our primary energy consumption continues to grow, the Earth system itself will regulate us. It will bite us on the backside. As atmospheric CO2 goes up, for example, negative feedback loops will kick in. Ice sheets will melt, for example. They're already showing signs of this in the West Antarctic and in the Greenland ice sheet, of course. Sea level will rise. It's already rising, of course. But by 2060, 1.4 billion people will live in the low elevation zone near the sea. China, India, Bangladesh, Indonesia, Vietnam are the most exposed to this zone. But of course, all countries are exposed too. Where will those people go if they're displaced by sea level? We can't even manage the displacement of very small numbers of people. How will we manage this? Of course, also, the world's deltas will disappear. If sea level rises at projected levels, there will be no major deltas, no major coastal deltas on planet Earth by the end of the 21st century. That's a really significant statement, but it's founded in fact. So think of the Ganges Delta. There are 100 million people live on it. Many tens of millions of people more rely on its agricultural produce. What happens to them when they're displaced by sea level rise? And what happens to the agricultural produce that other people depend upon? Of course, they're also not just habitats for humans, they're habitats for huge biodiversity. Deltas are incredible settings for biodiversity. They often act as nature's airports, for example. They're places where birds stop over as they move from one ecosystem to another. And in the Sundarbans, for example, we're already seeing increasing salinity due to rising sea level. It's lost much of its surface area. Its mangrove systems are now degraded and likely to lose 75% of them by the end of the century. And of course, these are also habitats for iconic animals like Bengal tigers. This needs a radical rethink of our relationship with nature, which needs to be mutualistic and not parasitic. Otherwise, our systems will collapse. Okay, we can't return to a hunter-gatherer lifestyle. because models suggest that that could only support about 10 million of us. And of course, there are 7.8 billion of us on this planet. We also know that many urban civilizations have failed. I talked about Çatalhöyük at the very start, that village in Anatolia. It lasted for about 1,000 years. And one of the explanations for it failing eventually is that it outgrew the produce of its local environment. That, of course, is implicated in the demise of many urban civilizations. The Indus Valley civilization, for example, disappeared about 4,000 years ago, again, possibly because of overconsumption. Tikal, the lowland Maya cities, also disappeared around about 900 AD, CE. But of course, these civilizations didn't fail completely. The people did adapt. There's very strong evidence that they adapted to a different lifestyle in many cases, or that they moved to other regions. Mayan civilization didn't collapse in the 9th century CE. Many of the Maya moved to coastal cities, and of course it was the Spanish invasion, Spanish colonialism, that caused the eventual demise of Mayan civilization as late as the 17th century. So civilizations have failed, but actually many people have learned to adapt by living in smaller settlements in a more sustainable kind of setting. So there are precedents for how we can survive, even if we get to the stage where some of our civilization begins to collapse. But there are also in history some remarkably good examples of sustainability, where people have lived in a very good relationship with the rest of nature, even in sophisticated, technologically advanced urban civilizations. A good example of this is Tokugawa, Japan. This is Japan during the Edo period, from 1603 to 1868. It's the period when Japan closed itself to the outside world because Japanese had seen what had happened in East Asia. They knew that if they let the Europeans in, the Europeans would colonize them and subjugate them. So they closed themselves off completely. That meant that Japan was closed to a source of external commodities. It had to recycle materials to survive, and it did that extraordinarily well. It developed a whole system of trade based on recycling, with artisans mending pots and pans and ceramics and clothes. It was a circular economy. Not only that, the few Europeans that did travel to Japan noted how incredibly clean Japanese cities were. Any of you who've been to Japan will know that that's still the case at present. It's the cleanest country on the planet by a very long way. It was very clean, also in the 17th and 18th and 19th century, because the Japanese recycled the materials that they thought would be useful for their agriculture. Night soil was a premium product. It was collected and sold by merchants. Of course, it's poo. It was shipped out of Edo, out of Tokyo on barges, and it was recycled onto the land. Another circular economy, giving back what's taken away. The Japanese were also right at the forefront of developing very good land use practices. They realized right from the start that vegetation, that trees in a city, for example, could regulate the local climate and could actually improve that climate for the inhabitants. Tokugawa Japan is not a panacea. It was hierarchical. It had members of its society which were effectively untouchable, the Hainin and the Eta, who were involved in professions that the Japanese considered as abhorrent. So it's not a perfect society, but in terms of its ability to sustain itself over 250 years, it did an extremely good job of that, based on a limited range of materials and on developing a circular economy. So it is possible that sophisticated civilizations can work like this. This is the one horrendously complicated figure that I put into this talk, and I absolutely do not want you to assimilate this, but I want you to just notice that these are a series of circles of the way in which we can recycle water in our cities, the way in which we need to predicate our cities and our civilization on renewable sources of energy, that we need to practice what the Japanese did, and when we take materials out of the lithosphere like metals or clay, we recycle them. We don't dump them, but we have industries that actually recycle them in a way that makes them available again to the system. That we don't dump dirty air into the atmosphere, and actually also that we have a new sphere which is conducive to supporting everybody. The new sphere might be a new term to you, but it's an idea that came out of the great Russian Ukrainian scientist Vladimir Vernadsky, who really is the inventor of the idea of a biosphere. And the new sphere is the sphere of human consciousness. It's very clear that societies where there is some degree of equality, where people are well educated, where their opportunities are enhanced, and where there are many different ways of seeing the world and doing things, are more resilient societies. That's clearly evident from the archaeological record of those civilizations that survive and those civilizations that fail. And that also maps on to the biosphere, if you like, that again, enhancing biodiversity will enhance ecological resilience. It will help us to preserve the biosphere going forward. At the very end of this talk, I just want to focus on the biosphere. I'll give you a few more facts about how we try to close this loop. So we're a long way from doing this, but we have to do this quite quickly. Let's just have a look at the biosphere. I don't know if any of you know Pembrokeshire well. I love Pembrokeshire very much. This is the island of Stockholm off the coast of the Marloes Peninsula in southwest Wales. It doesn't have any trees on it, which is curious because the name Stockholm means island with trees in Norse. And of course, there were trees there once upon a time. We know that because there are bluebells growing on the island now. And that's a giveaway of what was there ecologically in the past. We cut down all the trees because we wanted to put animals on here for pastoralism. And that is a microcosm of what we've done on planet Earth. It's certainly a microcosm of what we've done in the UK, where there are virtually no natural forests left, and all of our indigenous ecosystems are effectively severely degraded. But I want to give you some figures. Dairy and cattle only contribute 20% of the calories we need to survive. If everyone adopts the meat-rich diet of some countries, the USA, Argentina, Brazil, for example, Australia, we have to deforest the entire planet to sustain that. But if we adopt an Indian diet, which has much less meat in it, we could restore huge areas of wilderness, perhaps 50% of the land we farm. And that would be good for the biosphere, but it would be also good for us. Because if we don't, we can't sustain our relationship with the rest of the biosphere and the Earth system. We need to learn from cultures that at one stage we belittled. As Europeans, we thought we were superior to everybody. And yet the Martu in the Western Australian desert and indigenous people have learned to foster biodiversity. This is a position which is accorded to the older women in this culture. They actively nurture biodiversity. They go and burn back some of the vegetation. That burning back allows a greater range of plants to grow and survive. And that in turn fosters a greater range of animal diversity, which feeds back into the Martu because they like eating these lizards. So they get more lizards. So this is a win-win situation. Now compare that to what Europeans did. We introduced rabbits, and that rabbit-proof fence cuts across the Western Australian desert right through the Martu's territory. It's a good example of where the Martu were much better at understanding their environment than the Europeans that later arrived and colonized it. It's not just the Martu, but many indigenous peoples have a very good relationship with the food that they consume. This is a quote from Leslie Marmon-Silko, who's a Laguna Indian from New Mexico, but she's also an academic. And I love this quote. I carried with me the feeling I'd acquired from listening to the old stories that the land around me was teeming with creatures that were related to human beings, related to me basically. So that here is a close relationship between us. We understand ourselves as part of the rest of nature and not as something different. And I love this quote too. When the hunter brought home a mule deer buck, the deer occupied a place of honor in the house. It was decorated with silver and turquoise beads hanging from its neck. Silver rings and braces decorated its antlers. People are eating these animals, but they have an affinity with them. They feel that they're part of them, part of nature with them, and they take what they need, not more than what they need. And there's a really important lesson there for all of us. That's not the relationship that you and I have with a broiler chicken when we go to the supermarket. I don't think we even think about the life of the chicken very often. It's definitely not the relationship that you and I have with a burger either. But there's something to be learned from this relationship of of indigenous cultures with the way that they see the food and nature around them. Rewilding means trying to leave half for nature. This is a famous idea of biologist E.O. Wilson, but he's right. If we don't do this, we're going to be in a very, very serious situation very soon. I want to leave you with 3 possible trajectories. As a geologist, I've got to do this. This is if you come back in 100 million years, you can see what we did in the geological record. 3 possible trajectories going forward. Human changes to the biosphere are short-lived and unsustainable and marked with a mass extinction. There is a high probability of that. We know that. Another one, which is more in the realms of science fiction, is that the technosphere evolves to become self-sufficient and subsumes or supplants the biosphere. So now we're in the realms of Metropolis or of Terminator. Very, very low probability, because the technosphere is appallingly bad at recycling the things it needs to survive. It's akin to a forest fire, and it's going to burn itself out very quickly if it carries on with the pattern that it has at present. So I don't think that's going to happen. The one that we have to do, and we have to do very fast, is that we have to develop a mutualism between the biosphere and the technosphere being part of us also, to evolve it to a sustainable state, which can then persist over geological timescales. And that's what I've been trying to argue with you at the end of this talk. Even if we do that, it is still the case that as a species, we have fundamentally changed the biosphere. It's a fundamental change that will be recorded in the geological record. It is perhaps one of the biggest changes in the history of the evolution of the biosphere. So whatever we do, we are fundamental actors on the stage of geology on this planet. There's one thing I want to leave you with, and it's a quote from Carl Sagan. It's from his book, Pale Blue Dot. That is us. That's where we are. There is nowhere else for us to escape to. It's a pipe dream that we can go and colonize other planets, at least at this stage in our technological evolution. And Carl Sagan said this is where we make our stand. And that's absolutely the point I want to finish on. Thank you very much for listening to me. I can hand back to Richard now, I guess.